All right, so this is due November 29th. It feels like a long time away, but it's really not. So assignment 2. Assignment 2, you get to play with Goldbach's conjecture. So remember, Goldbach's conjecture is this idea that we can write even numbers as the sum of two primes. So 6 is 3 plus 3, 8 is 5 plus 3, 10 is 5 plus 5, 12 is 5 plus 7, and so on. And this has been confirmed up to some ridiculously large number. But we're going to write code to actually confirm it for 100 numbers starting with 1,000,000. So the goal of the program is to write some code that basically takes an even number and tries to write it as a sum of two primes. And if it succeeds, it should print out what that sum is. So for example, if you were to run this on smaller numbers starting with, say, 10, it should print out 10 equals 3 plus 7, or maybe 5 plus 5. And then it should go on to 12, and it should say 12 equals 5 plus 7, or 7 plus 5. But it should print out how each of these even numbers can be written as a sum of two primes. And there's a pretty straightforward way of doing this. There's a number of ways to do this, but a lot of them are incredibly inefficient. And since we're looking for numbers around 1,000,000, you want to do this pretty efficiently. So you need to be able to know if a number is prime or not, right? You need to be able to test for primes. So here's a pretty good way to do this. So write some number n. Let's just write n as a sum of two primes. Here's an algorithm you can use. Here's an algorithm you can use. Generate primes. So start off with the number 3, okay, and test n minus 3 to see if it's prime. And if it is, you're done. 3 plus n minus 3 gives you n, and if 3 is prime and n minus 3 is prime, right, then there's how you can write n. Okay, take the next prime 5 and test n minus 5. If n minus 3 was not prime, take the prime 5, test n minus 5. If that's prime, then print out that number, and you're done. If it's not, test the next prime, 7 and n minus 7, test 11 and n minus 11, 13 and n minus 13, and so on. And how do we generate these primes? Well, we can do that with another loop. So let's do something like this. I don't know, let's just go from I equals 3 to n. We know we're going to find a solution before too long, so let's just run I from 3 to n. If is prime I. So if I is prime, see if n minus I is also prime. Then just print out n equals the value of I plus the value of n minus I. And we're done. If 3 is not prime, right, skip all of this and just try I equals 5. So let's go by 2's. Try 5. 5 is prime. If n minus 5 is not prime, we'll go back up. Try 7. If n minus 7 is not prime, we'll go back up and try 9. 9 is not prime, so we'll skip all of this. We'll go back up. We'll try 11. Okay. This is efficient enough to do Goldbach's test on numbers around 1,000,000 in the blink of an eye. Right? You won't see a delay doing this as long as your is prime is written reasonably fast. But there's other ways that people try to do this that end up being really slow. For example, take the first two primes and add them together and see if you get n. And if not, take the first and third prime and add them together and see if you get n. Take the first and fourth. Do that all the way up until you reach n. Then take the second prime and add the third and see if you get n, right? That's a really, really expensive way time-wise to try to do this, because you're doing lots of calculations that aren't going to get you a solution. Right? You're adding basically random numbers and hoping that they end up being equal to n. And there's a whole lot of numbers that you can add up that will not be equal to n. Like this, you're only checking prime numbers and, you know, n minus that prime to see if it's prime. And this business of checking to see if something is prime, so see if it's divisible by anything other than itself and 1. So is it divisible by 3? Is it divisible by 5? Is it divisible by 7? Is it divisible by 9 or 11, and so on? And you only have to go up to the square root of n. And that's a big time savings, because for numbers around 1,000,000, the square root is about 1,000. So if you go up to the square root of n and you're just checking odd numbers, you've got 500 numbers to check. If you do odd numbers all the way up to n, you've got 500,000 numbers to check. So it's 1,000 times slower. So make sure you stop looking for factors once you get past the square root of n. You have to include the square root of n. 49, for example, is not prime, but you only know that when you try dividing it by 7, which is its square root. So you have to go up to things that are less than or equal to the square root. But after that, you're good. So the program should ask for a starting number, and should also ask for how many numbers you want to test. So you would start with 1,000,000 and you want to test 100 numbers. And so just throw this whole thing inside a for loop for I equals starting number, I less than starting number plus, you know, number you want to test times 2, I plus plus equals 2, and then just call your write function to write out each number, right? Or however you want to do it. This is just one way to do it. But the goal is you run your program, you can say I want to start from 1,000,000, I want to test 100 numbers, and it just writes out 1,000,000 equals this plus that, 1,000,002 equals this plus that, and so on. Okay, so write a function to see if a single number is prime will help you. Make sure you only go up to the square root of n. If you're careful never to try to use an even number as a prime, you don't need to worry about trying to divide by 2. Or you can just check if your number is divisible by 2 and it's not 2, it's not prime. You can use the modulus operator to look for a remainder when you do division. And so if a is divisible by b, then a% b will be equal to 0. So that's one way to test divisibility in C or C++. And then what you're going to turn in is a PDF, which will have 2 sections to it. The first section has got to have your source code in it. I got to see your program to grade it. Okay, so make sure your PDF that you turn in shows the source code. Okay, and then show me the output when you run that source code. Okay, so your PDF has 2 sections to it. One is the C code or the C++ code that you wrote, and then the output of running this on 100 numbers starting from 1,000,000. So it should be 1,000,000 equals this plus that, 1,000,002 equals this plus that, up through 1,198 equals prime plus prime. Put that all in the PDF, throw it up to Canvas. Is that clear what you're after here? And you can test this with small numbers, right? Just have it start from 6 or something, generate 20 sums, and make sure that everything it's printing out is prime and that they actually add up to what they're supposed to. And if you happen to find a number that can't be written as a sum of 2 primes, then you're going to be rich and famous. So don't have to worry about the homework then. All right, any questions on this? All right, well, let's do more induction. So let's prove that n is less than 2 to the n for all n bigger than or equal to 1. We kind of know this is true because 2 to the n's are big, right? 2 squared is bigger than 2. 2 to the first is 2, that's bigger than 1. 2 to the 10th is 1,000, that's bigger than 10. So this isn't really a very startling fact, but let's prove it using mathematical induction. So let P of n be the proposition n is less than 2 to the n. And this is what P of n says. P of n is not the proposition that n is less than 2 to the n for all n bigger than or equal to 1. That's not P of n, right? This is P of n. N is a variable, right? If n is 5, it says 5 is less than 2 to the 5th. If n is negative 6, it means negative 6 is less than 2 to the negative 6th, right? But what we're trying to prove is basically that P of n is true for all n bigger than or equal to 1. So we're trying to prove P of n for all n bigger than or equal to 1. So mathematical induction, we need 2 steps. We need a base case. So let's look at P of 1. P of 1 says 1 is less than 2 to the 1. And we can pull out our calculators and we can calculate 2 to the 1 is 2. And so this is true, 1 is less than 2. So P of 1 is true, just by examining what it says. So now let's assume P of n is true for some n. And it only has to work for some n bigger than or equal to 1. Well, since P of n is true, then we're assuming also that n is less than 2 to the n. That's the definition of P of n. So here's our ignore section. And I'm just going to write down what P of n plus 1 says. P of n plus 1 says n plus 1 is less than 2 to the n plus 1. Well, I know something about n versus 2 to the n. I can turn this into something about n plus 1 versus 2 to the n pretty easily by just adding 1 to each side. So I just added 1 to each side of statement 2. Now I know n plus 1 is less than 2 to the n plus 1. Well, I also know that 1 is less than or equal to n, because I'm assuming some n which is bigger than or equal to 1. And I know that n is less than 2 to the n, because we already stated that in statement 2. So in particular, 1 is less than 2 to the n, because that's how less thans work. 1 is less than or equal to n, which is less than 2 to the n. So 1's less than 2 to the n. That's just, I don't know, math stuff. It's the Latin term for it. So I'm going to plug this fact into statement 3 and say n plus 1 is less than 2 to the n plus 1 is less than 2 to the n plus 2 to the n. And that's just using 4 in statement 3. So I took this 1 and used the fact that it's less than 2 to the n. And what's 2 to the n plus 2 to the n? That's 2 to the n plus 1. So n plus 1 is less than 2 to the n plus 2 to the n, which is equal to 2 to the n plus 1. So n plus 1 is less than 2 to the n plus 1. And that's exactly what P of n plus 1 says. It says n plus 1 is less than 2 to n plus 1. Therefore, P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 1 because of mathematical induction. So we can show an inequality using mathematical induction. So we've done proofs where we showed that certain formulas were true. Sum of odd integers gives you n squared. Sum of all integers gives you n times n plus 1. We did a weird thing with tiling a floor with L-shaped tiles. We just did something that shows an inequality that always holds using induction. Let me show you a totally different kind of problem. Prove that n cubed minus n is divisible by 3 for all n bigger than or equal to 1. So n cubed minus n is always a multiple of 3. Well, if n is 1, n cubed minus n is just 1 minus 1 is 0. That's a multiple of 3. If n is 2, n cubed minus n is 8 minus 2 is 6. That's a multiple of 3. If n is 3, it's 27 minus 3 is 24. That's a multiple of 3. If n is 4, 64 minus 4 is 60. That's a multiple of 3. So we want to prove this works for all n. And if you know modular arithmetic, we can do this by looking at n, and n is congruent to 0, 1, or 2 mod 3, and we can come up with a proof like that. But let's not do that. Let's use induction and prove this. So as usual, we need a family of propositions, P of n. Let P of n be the proposition that 3 divides n cubed minus n. And if we plug in n equals 1, this says 3 divides 0, and we know that's true. 0 is divisible by any positive integer. It's just 3 times 0. So P of 1 is true. So now let's prove Pn gets us to Pn plus 1. So assume P of n. So 3 divides n cubed minus n. Okay, I'm going to need a big ignore section over here. So P of n plus 1 says 3 divides n plus 1 cubed minus n plus 1. All right, so who knows what n plus 1 cubed is? Off the top of their head.
N cubed plus 3n squared plus 3n plus 1.
Awesome. Pascal thanks you. All right, we'll learn next week how to do that, or the week after. Okay, so this is n plus 1 cubed. So n plus 1 cubed minus n plus 1. That's n plus 1 cubed minus n minus 1, which is going to be n cubed plus 3n squared plus 3n plus 1 minus n minus 1 is n cubed plus 3n squared plus 2n. If we can show that this is a multiple of 3, then we can show that this is equal to n plus 1 cubed minus n plus 1 and show that this is a multiple of 3, because this is exactly the same thing as that. And then we can say, therefore, p of n plus 1 is true. And then we can wave the mathematical induction hammer and say, therefore, since Pn gives us Pn plus 1, Pn's true for all n. So the question is, can we show that this is a multiple of 3? And there's no immediately obvious reason why it should be. Well, here's a 3n squared. We know that's a multiple of 3. That's just 3 times n squared. So is n cubed plus 2n a multiple of 3? If we can show that, then we can add 3n squared, and then we can say it's that. So this is all the ignore me section, right? This is just thinking out loud on paper. N cubed plus 2n, how can we show that's a multiple of 3? And when we're doing this, we usually need to come back and use the fact that we assumed p of n. In other words, n cubed minus n, we know that's a multiple of 3. Can we use that fact somehow to show that n cubed plus 2n is a multiple of 3? So any ideas? There's always a point in these proofs where you can get this far from one side, you can get this far in your ignore section, and you need to bridge that one gap. And then the whole proof kind of writes itself. So this is the point where those two sides meet.
Well, I would use the assumption and write 3k equals n cubed minus n for some k.
Okay. So we can definitely write that. We don't need that in the ignore section, because that definitely follows from 3 divides.
So that takes okay, so to that little bit over there, add n and subtract n.
So this is a classic trick in math: add n and subtract n, add 0 to something, but do a very particular form of 0 that lets you do something.
What we want to do is make something in what we've got on the right-hand side equal to look like the n cubed minus n on the left-hand side. So take that minus n and combine it together with the n cubed and replace that by 3k.
So we can move that minus n next to the n cubed and now ask, is n cubed minus n plus 3n a multiple of 3? And we know n cubed minus n is writable as 3k, so is 3k plus 3n a multiple of 3? What do you think? Is it? Absolutely. So somehow we've got a complete proof here, right? we've bridged the gap. We've shown, right, something that we can put in our proof. We can take it out of the hidden ignore column, right? So let's just work this backwards. We know that n cubed minus n is equal to 3k. So n cubed minus n plus 3n equals 3k plus 3n equals 3 times k plus n, and k plus n is still an integer. So n cubed minus n plus 3n is divisible by 3. And now we just have to kind of run up all of this stuff backwards, right? So 3 divides n cubed minus n plus 3n. And I'm just going to rewrite this a bunch of ways that are exactly the same algebraically. N cubed minus n plus 3n is the same as n cubed plus 2n plus n minus n, which is the same thing as n cubed plus, did I lose a square somewhere? Oh, which n cubed plus, I can add 3n squared plus 2n plus n minus n. So 3 divides n cubed plus 3n squared plus 2n. And so I'm up to this point. And so 3 divides n cubed plus 3n squared plus 3n plus 1. Take off an n to get back to 2n, and take off a 1 to get rid of that 1. So this is the same as that. And now we're just getting buried in technical details, like any good math proof. So 3 divides, and n cubed plus 3n squared plus 3n plus 1 is n plus 1 cubed minus n minus 1. And so 3 divides n plus 1 cubed minus n plus 1, distributing the minus sign. And this is p of n plus 1. So now you say, therefore p of n gives us p of n plus 1. Therefore p of n for all n bigger than or equal to 1 by mathematical induction and QED. And that's a really hard one to keep track of mentally where you are in this, because there's all this algebra that muddles up the scene. But the basic idea was, right, we're trying to show that n plus 1 cubed minus n plus 1 is divisible by 3. And we played around with n plus 1 cubed over here and found a way to use this fact that n cubed minus n is divisible by 3 to rewrite this as something times 3, right? And then once you have that, you have to sort of formalize it over here. So that's a different kind of proof, but it's still mathematical induction. All right, let's swing to the other extreme. Prove that if we add 1 to itself n times, we end up with n. If I do 1 plus 1 plus 1 plus 1 plus 1, total 5 times, I claim I will end up with 5. Do you believe this is true for all n bigger than or equal to 1? Have you ever proven it? Have you ever actually added a million ones together to see if you get a million? I haven't. But we believe this is true, right? And we would feel something was really wrong somewhere if there's some magic number of ones that when you add together, you don't get that number back. But most of us have never worked out a proof for this. And it's a hard thing to prove. It's easy to prove for a particular n. Just grab your calculator, put on the constant function, hit the plus sign n minus 1 times, and you get an n out at the end. But to prove it for all n takes something more. And mathematical induction is one way to prove this. All right, so let's make a proposition family. So P of n is the proposition that adding up n ones gives you n. And P of 1 we're pretty sure is true, because if we just add 1 with nothing else, we just get 1. We know P of 2 is true because 1 plus 1 is 2, and so on. So assume P of n. So the sum from I equals 1 to n of 1 is equal to n, because that's what P of n says. Well, let's add 1 more to both sides. So 1 plus that sum from I equals 1 to n of 1 is equal to 1 plus n, which I can commute. That's also equal to n plus 1. Well, when we looked at summations, we said that if you add this thing n times and then you add 1 more, we can simply rewrite this as the sum from I equals 1 to n plus 1 of 1. And that's equal to n plus 1. And that's what P of n plus 1 says. And so P of n implies P of n plus 1, therefore P of n is true for all n bigger than or equal to 1, QED. This part I may have cheated a little. If we want to be a little more formal about this, 1 plus the sum from I equals 1 to n of 1. I could rewrite that as a sum from I equals n plus 1 to n plus 1 of 1 plus the sum from I equals 1 to n. Right, I could rewrite 1 as just a sum where we just add one thing. And then we had a fact about summations, that the sum from I equals 1 to n plus the sum from n plus 1 to something is the same thing as the sum from 1 to that upper limit. And so getting from there to there, we might do a few more steps. But when you start getting this picky about things, where you're trying to not assume certain things, it's sometimes a slippery slope of like, well, what can I assume? Can I assume that summations work this way? Or do I have to somehow show that? So this is a little bit of a disturbing example in that sense, because we're trying to prove something that we feel is really fundamentally true, right? If you add 5 to itself 7 times, you get 5 times 7. If you add A to itself B times, you get A times B. Well, we can prove that using mathematical induction, using a very similar proof to this. All right, let's do a hand-wavy proof. Take a break from the numbers. Let's look at power sets. So prove that for a finite set S, the number of things in the power set is the same as 2 raised to the number of things in S. The cardinality of the power set equals 2 raised to the cardinality of S. And we've done this, we've discussed it, people discovered it on the board when we played with power sets. If I have a set containing 3 things, the power set should contain 2 to the third things, 8 things, 8 subsets. But we didn't prove it. We just kind of said it was true. So let's prove it using induction. So let P of n be the proposition. If the cardinality of set is equal to n, the cardinality of the power set is equal to 2 to the n. And this is for n, let's say, bigger than or equal to 1. We could do it for 0 too. All right, well, let's look at P1. So P of 1 says for a singleton set, S, the power set, has 2 elements in it. 2 to the first. Singleton set has 1 element in it. Well, I don't know if we can formally prove that in a really, really nitpicky court of law, but a singleton set is a set that contains one thing. Okay? The possible subsets are what? What are the subsets of a singleton set?
The null set itself and itself. The set containing, yeah.
Yeah, so the null set is always a subset of any set, including the null set. So that's always a subset. The set itself is always a subset of itself. Any other subset, right, if it contains no elements, it's the empty set. If a subset contains one element, it's got to be whatever that one element is that belongs to S. And you can't have a subset with 2 elements because there aren't 2 elements in S. There's only 1 element. So any subset has either 0 or 1 elements. If it has 0 elements, it's the null set. If it has 1 element, it's exactly S. So the cardinality of the power set here is equal to 2. And so this is true, although a set theorist would say you haven't really proven this in general. You just flapped your arms fast enough that people got bored of arguing. But we can take it as being true. But let's be a little more careful about the inductive step. So let's prove P of n gives us P of n plus 1. And we know once we do that, then we can say P of n is true for all n. So let's prove P of n implies P of n plus 1 for all n bigger than or equal to 1.
Can I make a comment?
Sure.
It seems to me like P of n should be the statement that starts for every S.
Yes, yes.
We are proving it for one S that we're not specifying which S. Seems to me like
So for any S such that the cardinality of S is equal to n, the cardinality of the power set will be 2 to the n. So that's a better statement of P of n. So we'll start the proof by letting T be any set of n plus 1 elements. And let's let G be a subset of T. Okay, so here we got to do something pretty controversial. I've told you that sets are unordered, but I'm going to ask you to pick an element from the set T. I don't care which element. Just pick one element, right? And it's got at least one element in it. It's actually got at least 2. So let T0 be one element of T. I'll make this a little T0. And I'll put a pair of eyeglasses here saying watch out for this. We'll come back to that in a second. Okay, so let T be one element of set T. T0 be one element of T. Okay, pick any subset G of T. There's two possibilities. One possibility is that T0 is an element of G. The second possibility is T0 is not an element of G. Agreed? Either T0 belongs to it or T0 doesn't. This T0 is fixed throughout the rest of this proof. Some magic T. If it's integers, I could pick the smallest integer, or I could pick the farm animal that weighs the most, or whatever, right? Pick some element and fix it. Okay, how many subsets are there that contain T0? Well, suppose we take the set G and we take away the element T0 from it. We're left with a subset of T that does not contain T0. Right, so every subset here corresponds to a subset in this case. And any subset over here does not contain T0. If we add T0, we get a subset of T that contains T0. So however many subsets we have over here, we have exactly the same number of subsets in case 2. Now, how many subsets of T do not contain T0? Well, a subset that does not contain T0 is a subset of our original set without T0. Right? If we take our original set T and we just toss out T0 and we look at any subset of that, we get a subset that doesn't contain T0. And any subset that doesn't contain T0 is a subset of our original set T without T0. So the number of subsets in case 2 is the same as the number of subsets of this set. So the number of possible G's is the same as the cardinality of the power set of T take away T0. Well, if T has n plus 1 elements, how many elements do we have in the set T when we take away T0? That's just n sets. So n elements. And because we assume P of n, we know that if a set has n elements, its power set has 2 to the n elements. So tie all that together, the number of possible subsets that do not contain T0 is 2 to the n. And the number of subsets that do contain T0 is also 2 to the n. And there's no element in common to these two, right? A subset's either here or there, not both. And any subset is in either this first case or the second case. So the total number of subsets of T is 2 to the n plus 2 to the n, which is 2 to the n plus 1. And so we've proven a set containing n plus 1 elements, the power set has 2 to the n plus 1 elements. And so we've proven P of n plus 1. And therefore, Pn implies Pn plus 1, so Pn is true for all n. So that's mathematical induction, proving something that we already know. We know this from doing Boolean combinations in 250. We've seen this in set theory. But it proves that this formula, 2 to the cardinality of S, gives you the cardinality of the power set of S. So let me make a comment here. You got a long weekend coming up. So if you feel like getting distracted and not working on PA4 or physics or linear or something else, here's something that might kill a few hours. This step in the proof, I needed to pick an element of set T that I called T0. Is that always possible? Can we always pick an element from a non-empty set? I mean, if I give you a set of markers and I say pick one, you can do that, right? If I give you a set of numbers, could be finite, could be infinite, could be integers, could be irrational numbers. You can always pick one, right? And I'll just take this one. But how do you prove that that's always possible? And in some cases, we can do this. For example, if your integers are positive, we can say, yeah, you could pick the smallest integer. That works. If I allow your integers to be positive, negative, or 0, and you could say, pick the integer with the smallest absolute value. And if there's two integers with the same smallest absolute value, pick the positive one. Okay, that works.
Are you saying that to be able to pick one, we have to be very specific and say really exactingly which one we're picking?
Not necessarily, but I'm wondering, do we know that we can always pick an element? And if you could describe an algorithm for always picking an element, that would work. But if you had, and we can do this, right? If we had a bunch of shapes, we could pick the one with the most surface area contained inside. Or the letter, we could pick the one that comes first in the alphabet. But if you pick real numbers between 0 and 1, if that's your set, can you describe a way for picking a single element from there? Well, there's no smallest real number in that range. There's no largest. You could try to pick one in the middle. But for an arbitrary set, if I don't tell you ahead of time what those elements are, can you guarantee that you can always pick one? And the answer is no. You cannot prove that you can always make such a choice. And this is just for fun now. So we make set theory very axiomatic. We try to make set theory very formal so we don't run into things like Russell's paradox. And there's a branch of set theory, a style of set theory called ZFC. And there's another version of set theory called ZF. And these describe the axioms that we build set theory upon. So in geometry, for example, you build up on top of a set of axioms. Parallel lines never intersect. Between any point and a line, you can do something else, right? So you can form a version of set theory using these axioms that are called ZF, Zermelo and Frankel. You can form another version of set theory that you also throw in one more axiom C. This is called the axiom of choice. An axiom is something that we can't prove, it's something we have to assume. And the axiom of choice assumes if you have a set, you can choose an element from that set. But under the axioms under which ZF set theory is formed, there's no way to prove that you can always do this. So if we want to do things like say, okay, pick an element from the set T, call it T0, you've got to have this axiom of choice. And philosophically, that's a little disturbing. Because you and I know someone can hand us any set and we can always pick an element. We can just, pick one at random, right? But there's no way to formalize that. And nobody's been able to come up with a way to actually do that other than to say, let's just assume that there is a choice function. Given a set, gives you an element from the set. But a lot of proofs require such a choice function. And so you have to throw that in as an axiom. So you can Google that, look at the wiki page on it, and it'll take you into things like Zorn's lemma and all kinds of other good stuff that gets pretty philosophical.
Could you not just prove that there will always be an element of the set to be taken?
There will be an element of the set to be taken as long as the cardinality is at least
Right.
1. But the goal of picking a particular element, right? There's no...
This doesn't have anything to do with whether the set is finite or infinite?
I don't believe so. If it were finite and if these things were ordered, we could pick the first element, right? or the last element. But since these things are unordered, it's a bit of a quandary.
Well, isn't axiom of choice logically equivalent to the well-ordering theorem
Yes.
we studied earlier?
Yeah.
So we're hopelessly lost.
Yeah. Or hopefully lost.
Hopefully.
Yeah. So why does mathematical induction work? Right? Why can we swing this big hammer and suddenly say, just because we proved P of 1 and we proved P of n gives us P of n plus 1, therefore P of n for all n bigger than or equal to 1. Why can we do that? And the reason is fairly obvious if you work backwards from this. Suppose that we're given this and we're also given this, right? We've proven the base case and the inductive step, but suppose P of n is not true for all n bigger than or equal to 1, right? So suppose P of 5,731 is false. Because that's what it means to say that this is not true. It means there's some n for which P of n is false. Suppose P of 5731 is false. Well, you can work backwards and say, therefore, P of 5730 must also be false. Why? Because we already proved P of n gets you P of n plus 1. If P of 5730 was true, this would tell us P of 5731 is true. So as soon as we know 31 is false, we know that 30 is false. And we can repeat that step again and say, since P of 5730 is false, P of 5729 is false. And we can keep doing that until we get down to P of 2 is false. And so P of 1 must be false, because if 1 was true, that would imply 2. So therefore P of 1 is false. And that's a contradiction because we proved the base case, which said P of 1 is true. Ergo, this cannot be true. P of 5731 cannot be false, it must be true. And that number is not magic. Any finite number would work, it just takes you more steps. But we kind of need mathematical induction to use that style of proof to show that mathematical induction works. We can show that the first 5731 propositions will all be true, but how do we know 5732 is true until we actually do this for 5732? So without mathematical induction, how do we prove mathematical induction? So that uses something that Randy just mentioned, which is the well-ordering principle. And the well-ordering principle basically says if you have a set of positive integers, there is a smallest number in that set. So if you have a set of positive integers, there's a smallest number. It could be an infinite number of positive integers, but there's going to be a smallest number. So take the collection of all integers for which P of n is false, and the well-ordering principle says there's a smallest number, n, for which that will be the case. So we can find the smallest n for which P of n is false. And right there, we got a contradiction, because if we look at P of n minus 1, that must be true because it's smaller than n. But P of n minus 1 implies P of n, which means P of n must be true. So there's your contradiction.
Could you go over that again?
Yeah, I'll write it out. So suppose P of 1 is true and P of n implies P of n plus 1 for all n bigger than or equal to 1. And suppose it's not true that P of n for all n bigger than or equal to 1. Okay, so let B equal the set of all n such that P of n is false. So that's the bad set. The collection of all numbers n for which P of n is false. And it's a collection of positive integers. So let K be the smallest element of B. Okay, we know that K has got to be bigger than 1 because the proposition is true for 1, so 1 can't be an element of this bad set. So K is at least 2. Since K minus 1 is less than K, P of K minus 1 is true. Because if P of K minus 1 was false, then K minus 1 should be in our bad set, and it's smaller than the smallest element in B. Well, since P of K minus 1 is true, P of K minus 1 implies P of K minus 1 plus 1, which is P of K. Therefore, P of K is true. And that's a contradiction. So I should have noted up here P of K is false, because K comes from the bad set B. All right, let's do one more example from 250.
So what you just proved is the Morgans theorem implies
Mathematical induction. Yeah. We know De Morgan's theorem. We can use set operations, we can use logical operations. I'll do sets in here because we're in 215. But we know De Morgan's theorem is true. De Morgan's theorem is usually represented with two sets, A and B. So the complement of the union is equal to the intersection of the complements. Have you ever done De Morgan's on three things? It turns out you can generalize this. But why is this true? Well, it's really not too hard to show if you use clever parentheses. So A union B union C all complemented is equal to A union with this other thing, B union C, complemented. That's just associativity. And I'm going to use De Morgan's theorem and say, hey, I have two things I'm taking the union of. One of them is A, the other one is B union C. I'm just going to use De Morgan's theorem for two variables on that and say this is the complement of A intersected with the complement of B union C. That's just good old De Morgan on two variables. And now I'm going to use De Morgan's on this piece, which again is just De Morgan's on two variables. The complement of B union C is the complement of B intersect the complement of C. And I can get rid of my parentheses. And there's De Morgan's on three variables. This thing is equal to that thing. You think it works for four variables? Good bet. So the complement of the union of A, B, C, D is the complement of A unioned with one other set, which is B union C union D. De Morgan's theorem, two things that we're unioning taking the complement, that should be the same as the complement of the first, intersected with the complement of the second. And since we know De Morgan's on three variables, we know that the complement of B union C union D is just B bar intersect C bar intersect D bar. Clear your parentheses. There's De Morgan's on four variables. Will this work on 4 million variables? Do you want to prove it? No. Right? It would take a bunch of steps, but this is the smell of a proof that screams out for mathematical induction. We know how to go from one step to the next. If we can do this for 3, we can do it for 4. If we've done it for 4, we can use that to do it for 5. Mathematical induction just says, okay, let's do it for n, right? And use that result to show it for n plus 1. So let's quickly generalize this. Let P of n be the proposition P of n says De Morgan's theorem for n sets. And we know P of 2 is true. That's just good old De Morgan's theorem. And P of 1 is kind of trivially true. It says A bar equals A bar. So assume P of n is true. So we're given that. Let's look at n plus 1 sets. And let's throw in some parentheses. And so now I have two things that I'm taking the union of. One is this big long union, the other is just an plus 1, and I'm complementing. Let's use De Morgan's. This is just De Morgan's theorem 2. So this is the complement of the first thing. Intersected with the complement of the second one. And now if I use De Morgan's theorem applied to n things, which I already assumed, this complement of unions can be written as A1 bar intersect A2 bar intersect AN bar intersect AN plus 1 bar. And the statement that that's equal to that, that's just Pn plus 1. And so that proves the inductive step together with the base case that proves Pn for all n. And it's no different from what we did when we went from 2 to 3 or from 3 to 4, right? We just generalized it, and you can use some fancy mathematical notation to get rid of the dot, dot, dots and make it more formal. But we're basically just adding one more variable using the inductive hypothesis to break this piece up into an intersection, and then using De Morgan's on two variables to intersect with the complement of that n plus first variable. So mathematical induction, once you're comfortable with it, really kind of fits in well with intuition in a lot of cases. It's something that we can see, but we don't know how to prove it. A lot of times, that's a good setup for mathematical induction. All right, so let's look at a weird one. Let's look at pi fights. In particular, we're going to study what's called an odd pi fight. So what is an odd pi fight? You have an odd number of people. And each person is given a pi to hold. And everybody walks into a room and you pick a position to stand in that room. And you stay in that position. And when the whistle blows, you throw the pie at whoever is closest to you. Okay, and that's the whole way the fight plays out. So each person has a pie. When whistle blows, you throw your pie at the person who is closest to you. And the question is there anybody who does not get hit with a pie? Is there a survivor? So, n people, n pies, one each. Throw the pie at closest person. And one of the rules is the distance between any two people is unique. You don't find two people that are exactly the same distance apart, so there's always a unique person who is closest to any other person. You can't have two people who are exactly 3 meters away from you because you couldn't decide, right? So wherever you stand, if two people happen to be exactly the same distance, one of them has to move a little bit. So distances are unique. And the theorem is, in such a fight, there is always at least one survivor. There's always one person who does not get hit with a pie. So P of n is the proposition that someone survives a fight of n pies, n people. And we can prove this pretty easily with mathematical induction. So let's prove P of n for all odd n bigger than or equal to 3. Because a pie fight with one person is kind of silly. There's nobody to throw a pie at. So what does P of 3 say? It says that if 3 people go into a room and they stand at unique distances from each other and each has a pie, and each throws that pie at the person closest to them, somebody won't get hit by a pie. Somebody will survive. Well, depending on, that's not a very good picture. Let's make something extreme. If you look at the set of distances between people, so let's just call these people A, B, and C. We look at the distance from A to B, B to C, A to C. Since every distance is unique, there's going to be a unique smallest number among those 3 distances. Whichever 2 people that distance corresponds to, they're going to throw their pie at each other. Right? So if A and B are the closest to each other, A has got to throw their pie at B, B has got to throw their pie at A. Because you're supposed to throw your pie at the person who's closest to you. If B and C are closest to each other, B and C will throw it at each other. If A and C are closest, A and C will throw it to each other. In each of those cases, once these people have thrown their pies, there's one person left with a pie in their hand who has not been hit by a pie yet. Right? And I didn't say it, you can't throw the pie at yourself. Right? You throw it at the person closest to you. So if A and B throw their pie at each other, person C will throw their pie at either A or B, and C survives. If B and C are closest, they throw their pies at each other. A throws their pie at either B or C, and A survives. And if A and C are closest, they throw their pies at each other, and B throws their pie at either A or C, B survives. So the proposition is true for 3 people. Okay, so now assume P of n. So n people, n pies. And now let's imagine n plus 2 people. And n plus 2 pies. Okay, same thing. Let's start off. Let A and B be the two people closest to each other. So A will throw their pie at B, B will throw their pie at A. So here's the whole room full of people. Here's person A, here's person B, it doesn't matter where I draw them. And then we have n people and n pies left in the population. So A and B will throw their pies first. They throw them at each other. They've both been hit in the face with pies. Now we have n people and n pies left. There's two possibilities. The first possibility is that one of these people at least throws their pie at either A or B. Right? One of these people might be really close to this person A. They might throw their pie at them. Okay, so if any of the remaining n people throws at A or B, let them do that, and then we have the following situation. We still have n people who have not been hit. We have n survivors, and we only have n minus 1 pies left. An accounting argument will tell you if you have n people in a room and n minus 1 pies, and each person throws their pie at one person, somebody's not going to get hit by a pie. Only at most n minus 1 people could get hit. So you're going to have a survivor. So someone survives. The more interesting case, though, is nobody in this remaining group throws their pie at either A or B. All right, so this is case 1. Case 2, the remaining n people only throw at each other. Well, we've got n people with n pies doing an odd pie fight, and we've assumed P of n, so there's a survivor. So someone survives. So if we assume P of n, we've proven that if n plus 2 people have n plus 2 pies and they do this pie fight, there'll be a survivor. So we've proven P of n plus 2. And that proves P of n is true for all odd n.
Could you prove this in one step by saying that there's somebody who's farther away from n, like has the furthest distance between, and then say that they throw their pie at somebody else, but nobody throws their pie at them? Or is that to say that there's...
The person farthest away...
But I guess they could have somebody who's closer to them.
Yeah, so they might be the farthest distance from anybody, but they might not be the farthest distance from everyone.
Right.
That's interesting, though. It feels like maybe there's a way to do it that way. All right, so that's a very different flavor of thing we're proving with induction, right? All right, so we got 6 minutes. Let me leave you with something to think about. So let's prove all horses are the same color. So if you've seen a brown horse, every horse in existence is brown. Okay, so let P of n be the proposition. In a group of n horses, all of them are the same color as each other. And we'll prove a base case in an inductive step, and therefore we'll prove P of n for all n. So if you took a collection of 1 billion horses, they would all be the same color. So however many horses there are on the planet, they've all got the same color. Okay, what does P of 1 say? P of 1 says, in a group of 1 horse, every horse in that group has the same color. Well, that's obviously true, right? Any collection of 1 horse, in any collection of 1 horse, all horses in that collection are the same color. And since there's only 1 horse in that collection and it's the same color as itself, right, this is trivially true. Okay, so assume P of n. Assume that given n horses, they're always the same color as each other. Okay, so let S be a collection of n plus 1 horses. And I'll make a little horse corral here. And I'll label these horses 1, 2, 3 up through n and n plus 1. Okay. So there's our horses, and they're standing still for the sake of this experiment. Well, how many horses are there in this collection? This is n horses. And because we're assuming P of n, all of these horses are the same color. How many horses in this collection? All right, this is also n horses. And all of these horses are the same color because P of n is true. But any of these horses in the middle belong to both of these sets. So all these horses are the same as, say, horse 3, and horse 3 is the same color as all of these horses. So all n plus 1 horses must be the same color as horse 3, which means they're all the same color. And so P of n plus 1 is also true. And so P of n implies P of n plus 1, and therefore P of n is true for all n. So that's it. All horses are the same color. So that's one you can think about if you don't decide to look up axiom of choice or Zorn's lemma. And we'll detangle this next week. So holiday on Monday, so no Clark classes. Wednesday I'm out sick, so no class here on Wednesday or in 224, so we won't meet again until Friday. So it'll be a week. I will post some induction problems, and they will be due a week from Monday. So I'll post those over the next day or two, and I'd like you to look at them and play around with them and think about them, and then bring questions on Friday. And Friday we'll mostly work on induction. And then the following week, which will be week 9, we'll start doing combinatorics, and then we'll go on to formal languages and automata. All right, so have a fantastic break, and I will see you sometime next week.